Okay, hope you all are getting ready for the exam, but as everything, this course just kind of marches right along. So we'll do 2 lectures this week just with new material. I have to finish up. I didn't get through all the material from last Thursday though, so let me finish that up and then move into today's material. So you recall last time we started talking about the idea of processes, the idea of one computer can execute multiple independent jobs, running programs known as processes, by switching between them and generally doing so at a rate that's so fast that you as the user don't really observe the changes, the difference. And then we mentioned the sort of, from a programming perspective, the way you create processes, new processes, is by a call to fork. And fork is a very odd function in that you call it once, but it returns twice. It returns once to the original executing process, which is called the parent, but it also then spawns a new process with a complete replica of all the state, including the program, whatever data has been created, even the state of the stack at that point. And that's called the child. And then when the function returns, it's returning either into the parent or into the child. And the way you can determine which is what the return value of fork was. It's 0 for the child. It's the process ID of the child for the parent. So the end of life of a process is that it terminates. And it actually goes through a 2-step process that it first terminates and then it is reaped. And so the term, there's a term called a zombie of a process that is terminated, meaning it stopped its execution, but it still exists in the eyes of the operating system. And it has to be, it's still consuming resources. There's various tables, sets of files, and so forth that the operating system maintains for all processes that are either, including these zombie processes, that until they are reaped, that's when the operating system is basically reclaiming the space for them. And so normally this is done when you wait for a process, or when a parent exits. When you wait for a process, and we saw there's both wait and wait PID as function calls that you can do, that the parent can just wait until its child completes. And when part of the executing wait is the operating system will reap that child. So that's just sort of normal when you do spawning a bunch of processes and then they all come back. And you wait for them, then this zombie business isn't really an issue. But it's a problem, and we'll see examples of it today, that if the parent doesn't wait for a child to finish, and instead it just returns, well, when the parent actually exits itself, when the parent itself terminates, then it basically passes the responsibility of reaping to the initial process, and it will do it for you. But the problem is for a parent that runs forever or for a long term, such as a server, a web server, or any service that you set up, and it's a program that has no definite stopping point. If along the way it's been spawning children, and those children have been finishing, but they haven't been reaped, then they all become zombies. And that can, over time, of days, weeks, months, however long this server runs, it can actually basically clog up the whole system. One of the reasons you'll notice that the Shark machines reboot every 24 hours is because a lot of students do this in the next coming lab, the Shell lab. They create these zombies that are floating around, and so basically by rebooting the system once a day, we kind of flush out all that stuff. So it's a sort of a very drastic way to deal with this issue. So here's an example of some code that you see it calls fork, and within the child just exits. But the parent doesn't really do anything. The parent just runs forever. So not a very exciting program, but it demonstrates this idea that the parent hasn't done anything about its terminating children. And if you run this program, and by the way, I'm going to give up trying to do demos of programs. It seems like it's just too many clicks on a screen and takes too much time. But I recommend all the code for this is on the website, or reachable via the website, all compiled, ready to go on a Shark machine, or you can copy them yourself and compile them yourself. And so I recommend you sort of play with this just to convince yourself that this is really what I say is true. But what this example program does then when it starts is it fires up the process, it calls fork, the child terminates, or it says it terminates, and the parent runs. But now and you'll see that this invocation here of forks that I'm showing here, I put an ampersand at the end of the command line, and that says, do the command, execute the command, but do it in the background. So return back to the shell and just let this program run. And this will be a very important concept we'll talk about today. And what you do then, if you run PS, which just is process status, it lists all the processes for you right now, and there's various command line arguments to it, but this is the basic version of it. It lists all the executing processes, all the processes that you have. And you'll see that it shows two that are labeled as forks. And you'll notice the process IDs, that 6639 is, whenever you run a background, the shell, the interface you have, the command line interface that you have to the system will print the ID of the process that was just created. And you'll also see that the program said, oh, and by the way, the child has process ID 6640. And you'll see that here we see two processes, 6639, which is the parent, and 6640, which is the child. And here the notation that it's defunct is an indication this is a zombie process. It's terminated, but its resources haven't been reclaimed yet. It's not yet been reaped. Now, if we kill this process, and in this case we do it explicitly with a command where you just say kill, and then you give a process ID, then it will terminate the parent. And in doing so, the zombie child sort of is then inherited by the main initial process of the system, and it will do the reaping. So by killing the parent, it also knocked out this zombie child. So that's what I mean, that from a programmer's perspective, this is only an issue if the parent were something like a server where it wasn't going to run, where it could run for an indefinite amount of time and could create a bunch of children that don't get reaped. Just to show you an example of a sort of similar idea is, here's one where the child has an infinite loop and the parent exits immediately. So it's sort of the flip of the two from before. And you'll see that I actually don't have to put the ampersand on this one because the parent is going to return immediately, exits immediately back to the shell. But if I do a PS, I'll see that there's still a forks process, and it has a process ID 6676, which is the child. So the point is that this child is going to keep running, and it's not a zombie, it's an active program doing just spinning in a loop, doing nothing useful, but it's still executing. And that will run again, potentially forever, unless somebody kills it. And the way to do that again would be, for example, to use the explicit kill command to the shell. So you see that the idea of a zombie only happens when a child exits, but is not reaped by its parent. If the child runs forever, then even if the parent exits, it will, that child will continue running. So I don't know if we really talked about the weight function, I guess. But the idea of a function weight, which I guess we've mentioned sort of tangentially a couple times now, is for a parent to basically hang up and wait until one of its children has completed. One of its children is terminated. And so this form of it will wait if it's forked 20 children, then any one of those will cause it to return from this function. So wait's the first example we've seen of basically you've seen it in other places, where basically the program is just going to hang up or hang there and wait until something happens. And the way that's actually implemented is it's by this syscall mechanism that when it calls wait, the program will just basically willingly suspend itself until the operating system, don't do anything with me until something interesting happens. And then when later the child completes, that will, and the operating system is dealing with the fact that child is called its exit process, exit function, then it will recognize, oh, there's somebody waiting for this, and it will return back to the program, that the parent that's waiting. So in the meantime, it could do various so you can call wait, and the operating system could go off and run any number of different processes before it returns. And you can get various information, the status information about the child in this. And so this shows an example of a program that explicitly waits, that the parent explicitly waits for its child to exit before it continues. And you can see that we use this graph representation to show this idea of these edges become constraints, that the parent program will not continue past this point until the child is completed. And so this is, again, one way you can see that it controls the concurrency, the kind of possible executions this program could have. That it's impossible for the program to print by here without having previously printed HC, the hello from the child, because wait will only continue past this point once the child is executed. In general, this example would demonstrate that the waiting, when you say wait, it doesn't presuppose any particular order in which processes will complete. So they can happen in any order. And so this example shows, and this is actually, no, this code's okay. We'll look at similar but buggy code later. That when you wait, this example shows firing up n different processes, where I think n is actually 5 in the program. It will fire 5 different children, the parent will, and then it will wait for them in a loop, one after the other. But the point is, they don't all have to return in the order they were created. On the other hand, there's another version of wait called wait PID, where you can actually specify which process ID you're waiting for. And by that way, you can force it to follow this in a very specific order. There's not a whole lot of applications for that, but it's an available possibility. So that's the sort of key ideas behind the idea of forking, waiting. And now there's another interesting function called which goes under the various name of exec. There's different versions of this, and this is the most general. It's the way that a new process, once a process has been created, it's told to execute a specific program. So exec is sort of like a high-level way of saying, execute this program using these command line arguments. So it's given the file name, or technically the path name of a file that contains executable code. And it's given, just like you've seen for the main function, it's given the list of arguments that this program's supposed to execute on. And then it's also given a third list, basically array, of the values of the current set of environment variables for this process. And you've seen examples of environment variables. For example, the one path, uppercase path, determines the order in which the operating system chooses how to find a program if you just type in the name of a program. And there's a bunch of other environment variables out there. So the point is that every process as it begins can access and determine what is its information about the operating environment that's encoded in these variables. So in general, file name is the name of a program, and that can either be a binary executable file, or it can be some type of script. If you've ever looked at the beginning of a script, say in Shell script or Python or Perl or any of those languages that support scripting, you'll see it begins with a pound sign, exclamation mark, and then the path name, the location of the interpreter, like Python, Perl, Bash, or whatever scripting interpreter exists for that. And so again, that can that's how you can sort of set up a script and have it executable by telling it what interpreter to use for it. And then you know about the idea of argv as being an array of strings, and by convention it's supposed to be set up with the first string being the name of the file. And then the list of environments is similar to the argv list. It's a list of, except that it has it's actually a list of, it's like a keyword value pairs. I'll show you this with some concrete examples. But the interesting thing about execv is it's another one of these functions that has a strange calling that normally it gets called once and it never returns. Because the idea of it is I've created a process by fork, and it's now a copy of the parent. What I really want it to do is execute some completely unrelated program and terminate. And so what happens is at the top level you call exec, and that will load up and begin execution of this new program. And then if everything's going fine, it will never return back to this point again. It will just exit when it calls its exit. The only time it returns is, for example, if the file name is not a valid program, it will return with an error code. So this is a picture sort of illustrates how this information is all stored in memory, so that the list of arguments is encoded as a null terminated list of strings, and the list of actually strings meaning pointers to each of these is really a pointer to an array of characters. It's not the characters themselves. And same with the environment. It's a null terminated list of environment values, each of which is a string giving the name of the environment variable and its value. And then and what it will do is then, excuse me. So this is an example of calling, setting up a call to exec. And what I want it to do is call the ls operation on some with some command line arguments. So ls, as you know, is a command within the shell that you can use to list files. ls, rm, mv, all those. There's actually, for every one of those commands, there's actually an executable file that implements that command. And it's generally in the directory /bin/ whatever the name of that command is. So by saying I want to execute the program that's stored in /bin/ls, that's just the way of saying I want to call the ls command. So what you'd do is you'd set up a set of, if you wanted to do this call, is you'd set up an array of 4 pointers, the first of which points to this name /bin/ls, the next and then to the command line arguments, and then the final one is a null pointer. And similarly, there's already an existing set of environment values that's maintained by the operating system. You don't have to create that yourself. And then you'd call the exec using these various arguments. And if it returns, it's actually a sign that something went wrong. But normally it doesn't return. So we'll come back to that now. So that was the sort of tail end of the lecture from last time. Let me move forward with the material for this time. Any questions up to now? Yeah.
So what's the point of making sure that it's a child that's running the program? So like, what's the point of the outer if statement?
Oh, so the question was, why is in this example here, is it doing this test, is the PID equal to 0? Because, and we'll show, this is sort of a little snippet in a bigger context that we'll see shortly. But what's happened is the parent the parent for some reason wants to run a new program, which normally wouldn't be to just list files, but it basically wants to fire up something and do something with that information. And so the parent calls fork, and now that it's got 2 processes, one of which is the original parent, and another is its exact clone is the child. And so I really want the child to do this, execute this new program. The parent, if it were to call exec, would sort of call exec and never return, and so it sort of loses its flow of control. This will make more sense just shortly when I tell why a context where you call exec. So this is the example from before. And so remember, we're starting now the nominal material for today, so it looks like there's sort of this introductory part. So last time we talked about this idea of exceptional control flow. And we talked about this sort of idea of, at some very high level, how these ideas of processes are maintained by the operating system. And what we'll look at today is what are called signals, which are ways that you as a programmer can sort of create and handle some of these exceptional events. So it's like a software interface to this mechanism that's used to control the execution of processes by the operating system. And then there's a whole other section, non-local jumps, which there's slides at the very end of this lecture that we won't have time to get into, and they're covered in the book, but they're a little bit less sort of central to the discussion, so we won't try and talk about them. But there's some pretty good uses of these non-local jumps. I think I mentioned it to you last time. It's a little, if you programmed in Python, Java, even C++, all of those have some kind of exception handling mechanism where you can try something, and if something goes wrong or there's an unusual event, you can say, handle it this way. Come back to this point and handle it. That's not really built into C, but there's a system library with these functions called set jump and long jump that allow you to get a sort of very primitive version of exception handling. So as we said at the beginning on exceptional control flow, that there's some exceptions are synchronous, meaning that they're part of the executing program, and some that are asynchronous, meaning that they're caused by the external activities in the system. And signals are a way for users to handle some of these asynchronous events. So the way we're going to talk about it is with the idea of a shell. So I mentioned the shell is sort of the command line interpreter that you have when you're logged into a machine using a command line interface. And a shell is really itself a program that will fire up new processes every time it's given some command line to execute. And it will manage those processes in various ways. So when you log in then, you're given a shell, and every time you ask it to do something, it will create a child and to execute that code, and potentially that child will create more processes. So you get this whole tree of processes going. And if the system has multiple users logged into it, it will have, each of them will be running their own shell, and each of those shells in turn will have its children. So the whole system of processes then sort of has this tree-like structure, because some of these shells can correspond to different users, or if you log in twice to a machine, like through 2 different SSH connections, you yourself, of course, sort of have the appearance of 2 different users as well. And then there's some other processes that run in the background in a system that are known as daemons. And daemons are just ones that sort of sit there quietly handling things in the background for you. So for example, HTTPD is the web server if your system is running hosting a web page. There's ones that even for your laptops and things are managing network connections, for example, on your behalf. So that's the idea, that this idea of forking of children naturally gives you this tree-like hierarchy of processes. So a shell is, as I mentioned, sort of a command line interpreter, but it's also just a program, and it implements its actions by executing other programs. The original shell was just called SH. There's ones that were sort of made a little bit more fancy, C shell and TC shell, and then one called bash, which is the one that's sort of the default when you're running Linux. And you've probably heard this. Some people get very emotional about which shell are you using and things. I don't pay much attention to that. But you'll see in the book, and we'll cover a little bit of glimpse of the code, and actually you're going to write your own shell starting Friday morning early if you get the assignment downloaded fast. So your next coming assignment is pretty related to this. And it will partly help you better understand all this business about signals and processes and stuff. And also better understand what the operating system is really doing when you ask it to do things. So as I mentioned, this simple shell is available as a program online, linked to the web page for this lecture. And it's really simple. It doesn't do a lot of the nice stuff shells do. So basically you just start it, just like any other program, but now you'll see the single right arrows are the prompts being given by this shell that's executing as sort of a sub-process of your login shell. And you can give it the name of a program. It doesn't understand the sort of short version of arguments. You have to give the full path name of the file that implements each of the standard functions. But if you say, for example, /bin/ps, it will execute the ps command. And I can do a little, it handles a little bit of job control. For example, running some jobs in the background and others in the foreground. So I can tell it to sleep for 10 seconds, and if in the background, and then if I, within 10 seconds, say, tell me the processes running, you'll see that it will list sleep as one of the currently active processes. The only built-in command it understands is quit. Otherwise, you have to give these, basically, it treats everything you type as the name of a file and some arguments that you're passing to it. So I'm going to just show little pieces of the code for this to highlight some of the most important features. But like I said, this is not that much code, and you're going to want to go and look at it, and you're certainly going to want to understand it for your upcoming assignment. But the basic idea is it's just in an infinite loop. Well, a loop that potentially loops forever, where it prints the prompt to the command line, then it waits until you type something in, and it reads that in with the fgetS, and then it checks to say if it received an into file, then you want to exit. Otherwise, you want to evaluate this command line. And once it's done evaluating that command line, it will jump around and do the next. So it's a standard interpreter that you read something, you do something with it. And so let me just go through pieces of this. So the interesting function is this one called eval. And let me just step through parts of it. So there's some parsing that takes this command line and it breaks it into these separate fields to form the argv. An argv will be an array of characters that will basically be formed by breaking up the command line. And the simplest way to do that basically is to replace all the spaces with nulls. And now you have all these the command line is now broken into a series of separate strings. And I just have to create pointers to the starting places of those strings. So that's, I won't show the code for that, but you can imagine it's pretty easy to do. If it determines that this line is empty, it just ignores it. And then it checks, is this a built-in command? And as I mentioned, the only one that's supported is quit. And this function, which I'm not going to show because it's not very interesting, if it determines it's quit, it just exits the shell. Otherwise, what it's going to do, and this is where life gets interesting, and it relates to the question you were asking before, is now you'll see that what it wants to do is create a new process, its child, and the purpose of that process is to execute the file that this command line is telling it to. So it will call fork, and just like what we said before, it will call execve on this set of arguments, using argv of 0 as the name of the file to execute. And the environ is a global variable that encodes the environment variable information. Anyone can access that global variable. If it returns, that's a sign that somehow this was not a valid command, and so it prints the error handling here is rather primitive. It just says, oh, that's an error, and it just exits the whole shell, which normally is not a good idea. When you're starting to write programs now that do more than just some little thing, and so if there's an error, what really you should do is probably go back to the command line, but it doesn't. But this is an example of execve. If it returns, it's a sign that something's wrong, because normally this would never return. So this sort of completes, you see how the shell program, my interpreter, created a copy of itself via fork. And that copy now sort of takes on the role of executing this particular command, and then that's all it does. It exits out. But now we have this choice of, is this going to be a foreground or a background process? So a foreground is the default, but a background, if you put an ampersand at the end of the command line, you're saying, I want to execute this command, but I don't want to wait until it's done. I want the shell, to come back and be able to do more commands. So it says if it's a foreground process, meaning it's supposed to wait, you'll see that it does a wait PID on the process ID that it just created, the forked process. And presumably that will have an error. So this is the way that now the shell is going to wait for as long as it takes for the child to complete and then return back. But if it's not, if it's a background process, then you'll see that it just prints out information about the process it created, like I showed you in a previous example, and then it returns back from eval. And by returning back, now it tells this main command loop interpreter to, so okay, now execute retrieve the next command to the shell and execute it. So that's how, it's kind of interesting how simple it is, the idea of how you maintain a background process versus a foreground process. So that kind of gives you the very rough idea of what a shell is supposed to do. There's a problem though. There's a problem with this code that has to do with zombies. And for foreground jobs, it does fine because it will call wait PID. And when wait PID, the part of what wait PID does is the child terminates, and wait PID makes sure that child gets reaped, so it's no longer a zombie. The problem is if it was a background process, the shell just marches on and doesn't pay any attention to it. So even when the background process completes, it will never get reaped. And a shell is an example of a program that in principle can run indefinitely. And so if it keeps happening over and over again, it can accumulate this whole bunch of zombies. So how we handle that? Well, as you could imagine, there's some mechanisms for handling these kind of events, that's, as well as a number of other possible outcomes, using a mechanism called signals. So as I said, signals are the way that your software, your user programs can sort of generate and handle sort of events exceptional events between processes. So let's talk about signals. And signals is actually, this is what I'm showing you with this shell example is one use of signals, but there's multiple others as well. So a signal, it's a little bit funky, some of the details of signals, meaning if I were designing an ideal mechanism for communicating between processes, I don't think I would have come up with this one. But it's what it is. It's a standard that was created for Unix years ago, and it still exists today. So a signal is actually something that one process requests to deliver a signal to another process, but it's all managed by the operating system. And there's different types of signals. There's a small range of integers that identify possible signal types. And the only thing that the receiving process knows is that it got a signal of a certain ID. It doesn't know where it came from. There's no extra information with it. And so, as I mentioned, there's sort of a range of 30 different signals, and you can find that list in various places, including the book. The ones that are sort of the most, the ones we'll talk about today, is called SIGINT, meaning SIG interrupt. And that's what happens if you're running a program and you hit Control-C. You're basically telling the program, stop, don't, stop forever, terminate. And so that's, the way that's implemented as a mechanism is actually that when you hit Control-C, the shell is going to deliver is asking to deliver a SIGINT signal to the running process. Then there's another one called sig kill, which is when you saw me using the kill command on the command line. That's sending the sig kill signal, which is sort of more powerful than an interrupt. You've also seen ones like segment violation, and some of those are illegal instructions. Those are all signals as well. And then there's one called sig child, which is sent when the child sends that signal to its parent when the child terminates. And we're going to use that as a way of handling these zombie children in the shell. The other thing you'll see is that for each signal type, there is some default action, meaning if there's no other overriding information, how a process will handle it. And you'll see that a lot of them, what it will do is just terminate the process. The sig child signal actually its default is to just be ignored. The parent won't react at all if it hasn't set up some special way of handling this signal. So there's different options of default options: terminating, ignoring, or suspending, meaning like when you hit Control Z, you're stopping the executing program, but in a way that it can resume it later, as opposed to Control C, where you're stopping it forever. So just some terminology. We say that the kernel is actually the one that does the work of signals. And it delivers the signal to a destination by basically setting a bit in some field that says you have a signal of this type. And so signals can happen in various ways. One is if there's some system event, or one process has basically asked the operating system to deliver a signal. And there's this very misleading function and actually command called kill, which normally if you say kill, it means send a sig int, but you can actually use kill to send any signal type to any process. So just to sort of show this idea, it gets pretty involved here with some notation and conventions here. But if a process wants to A wants to send some type of signal to C, this is actually done, the operating system does it. But so the process A says, send a signal of this type to process C by using the function called kill. And now C has basically a little set of Boolean flags that you can see the idea of there being 30 different signals. It has a bit vector corresponding to an int, a 32-bit word, that is set to 1 if there's a signal of that type pending for this process, and 0 if there isn't. So the idea of sending a signal, what happens is the operating system just sets the 1-bit field for that particular signal number for this particular process. Meanwhile, C can maintain a mask, a similar mask, that lists which signals it's willing to accept, or conversely, which ones are blocked. So if this flag is set to 1, it means even if a signal of this type arrives, I'm not going to pay attention to it. But if it does, if this is set to 0 and that signal is set, then eventually the operating system will cause that signal to be delivered, and which will basically mean wake up this process and have it handle this signal. This will make a little more sense as we kind of wade into this more. And this model, by the way, of thinking of it as 1-bit flags turns out to be important. Because if, say, processes A and B send the same signal to C, before it gets handled by C, it won't queue them up. it won't say, oh, you've got 2 signals pending. It just says you have a signal pending. So that's one of the weird things that has implications from a programming perspective of signals. But eventually then, imagine this signal got set for C, and then process C now responds to that. And when it responds, something's going to happen. And as I mentioned, one of the possibilities is it will ignore it. So even though that signal was delivered, nothing happens. Another will be to just terminate this process. And a third is to execute a signal handler, which is a special piece of code that you as a programmer can set up so that it will handle particular types of signals for this process. And this is where it gets interesting, that you as a programmer can write signal handlers that tell the operating system how to handle different types of signals that might be arriving into your program. So the idea of it is the process is running along, doing whatever it's doing, and the operating system, for one reason or another, just decides, well, I'm going to tell it to run its signal handler. And so it will jump over and start executing the program or the code that's provided in this handler. And the handler might exit the whole program, but if it doesn't, if it just does a normal return, it will go back and resume execution of the original program. So the interesting thing about signal handlers, though, is it's still considered the same process that was executing before. So I'll get into that in a minute. So as I mentioned, this idea of at any given time, there can be some number of signals that are pending for a process, meaning it's been delivered but not yet received. And so those are the ones for which these little bit fields are set. And as I mentioned before, it's important to realize that they're just little 1-bit fields. So if there's multiple signals that get sent before they can be handled, they don't queue up. And as I mentioned before, it's possible to block certain signals as well. So, and in general then, the kernel for each process is maintaining these 2 bit fields. One is the set of pending signals, and the other is the set of blocked signals. And then, so how are signals sent? It's actually possible to send a signal to a specific process or to a whole collection of processes. And the idea of a collection of processes is that every process is part of a process group. And typically, when you're running as a user logged into a shell, your shell and every process that it spawns is part of a single process group. And so there's, for every process, there's an associated process ID, PID, and a process group ID, the PGID. Which is usually the process group ID is the PID, the process ID for the sort of highest node in this tree for this process group. And you can basically, you can change the process group of your program with a function called set PGID. So if you say the kill command, as I said, the default when you give a kill command is you give you just say kill and you give a process ID. But the more sort of exotic version of kill is if you give a negative number as the first argument, then that's actually the signal number, the signal type. So you remember from the table before that signal type 9 is a sig kill, right? So you can say basically deliver signal type 9 to something. And similarly, if I give a negative number for the process, negative number here, I'm saying deliver the signal to every process in the entire group, 24817. So in this case, I set it up so in this example, and you can look at the code, it had 2 processes in a group, and the group ID was 24817. So by saying kill -9 minus 24817, it will kill both of these processes here. So this example is showing a couple things. One is you can specifically identify what signal you want to deliver, and you can deliver it to either a single process or to a group of processes. And so in general, as you know, if you type Control-C, it will terminate whatever your program is running in the foreground. And the way it happens is you have the kernel send the SIGINT signal to every job that is in the foreground process group, including its children, possibly, in other words. And there's a similar, if you do Control-Z, that's called the SIG stop. And you can test this out. If you run this, it'll set up a process group with 2 running processes. If you type Control-Z and you say, what's the status? You'll see that and you use an argument W, which has to give a little more information. And it will tell you these 2 processes are stopped. And now if I okay, so I did forks, I typed Control-Z, that put these in I stopped these processes. And now if I say foreground and I type Control-C, then it will terminate those 2 processes. So the point being that Control-C terminates not just the process that's directly running, but if it spawned children, those will be terminated as well. Okay, so as I mentioned, this kill, so now kill is more than just the ability to kill other programs. It's actually a way to deliver signals of any type. By the way, if you tried to kill your friend's program, you'll find it won't work. You can try to deliver that signal, but the operating system might not let you. So here's an example of some code that fires off a bunch of children, or all of which just go into an infinite loop. And what I'll do then is I will kill them, meaning I'll call the kill function on their process ID, where the type of signal I'm sending is SIGINT. And then I can go through another loop that will then wait for those all to, what it will find is, since these have already been killed, that they'll all come back saying, oh, it was already terminated abnormally. So, general with wait, there's various ways you can look at the status information and determine something about the nature of that child and how it terminated. So signals are, it's important to recognize that signals are a way to handle, we've talked about this idea of the kernel. And so the kernel is part of the operating system's code that is used to manage processes. But when the kernel runs, it's not considered a process of its own. Instead, what happens is, as one process causes something that would cause the kernel to fire up, for example, it makes a syscall, or it gets interrupted by some external event, then the program will shift into kernel mode, which means it has various privileges to access data structures and do things that you as a normal user can't do. But at some point, if it's going to do a context switch, what it will do is transition. It will store away whatever state it needs about process Q and load up from somewhere in its memory information about process P. And then when it's got that all loaded, then it will begin executing the user code. So that's the normal context switch, is going between process Q and process P. So this is the point also at which it's going to handle any pending signals. So now what it's going to do is look at process P as it begins to get ready to fire it up. And it's going to say, hey, are there any pending signals for process P? And it will do that by looking at this sort of combination. Are there any signals that are pending that are not blocked? And then for each of those, so if none of those, there are no pending signals, then it will just begin executing the regular code for process Q. But if there are some pending signals, unblocked pending signals, what it will do is start to process each of those in priority order, starting from the lowest number to the highest. And it will it will force that process to receive those signals. And if there's no signal handler for that particular one, then it will do whatever the default action is for that signal. But if there is a signal handler, then it will invoke that signal handler. So this is the way that I'm trying to, it's a nice picture. Sorry, let me see here. Well, we're going to come to a nice picture. But the point being that when it executes process P, when it resumes execution of process P, it might, it will, if there's any pending signals, unblocked signals, it will do those first before it executes the normal user code. And that's how signals are implemented in a very simplistic way. So the idea being that your program's running along, perfectly happy, doing over what it does, and one of these signals sort of appears to magically come from outer space, that the operating system is taking control of your program and either doing a default action for that signal, which possibly means terminating the program, or it's invoking a signal handler that's sitting there as some code that's within your program already that you've put in there. And then as those signal handlers return and nothing else happens, eventually it will come back to your regular code. So there's a function called signal that you use to say, I've got some code called the handler, and I want you to use it to handle this particular signal number, which you give as an argument. And there's sort of predefined constants for the corresponding to possible default actions you can do, or it's the address of a function. So let's show a simple example that you might have encountered in the bomb lab. So if you tried in the bomb lab to hit Control-C, you might have seen this kind of creepy thing come out that it said, printed this threatening message from Dr. Evil, but then if you were patient, it would actually exit. And so that was implemented as a signal handler. And this, by the way, will show why this is not really a totally legitimate code, but let's set that aside very briefly. But this is sort of a version of what the program did. So what happened then is you type Control-C, but I'd already, before beginning your part of the part of the program you saw, I'd installed a signal handler for SIGINT, which is this function. So when you type Control-C, the operating system delivered the SIGINT signal to this program, but rather than the normal thing, which just terminates the code, it invoked this handler. And the handler then printed out this message. It used sleep to sort of pause for 2 seconds. And, but then eventually it called exit, and so it exited your program, which is what you wanted to do. So that's an example, and by the way, you can look at the code for the several of the labs we've done, and we've got signal handlers sitting all over the place handling. When it came back, said, oh, you caused a segmentation fault, or oh, you did something wrong, or oh, this code took too long to execute. Those were all implemented as signal handlers. So this is the slide I wanted to show. An important thing to recognize is we talked before about this idea of concurrency, meaning that you're interleaving the execution of multiple functions. But the main point is that the handler is considered part of the same process. It's not a separate process to handle a signal. And so it has access to all the same global variables and stuff that the main program does. And so what's happening is it's a similar idea to a context switch. So here's an example where A switches to B, and now as B comes back to A, it sees that there's an unblocked pending signal, and it executes the handler code for it. And when the handler returns, it returns back to the kernel, and potentially then it will just resume back to the original program. So it's possible for signals to interrupt. One signal can interrupt another handler. So it will get this sort of nested thing. But it's important to recognize that once a signal happens, it either returns or it calls exit to the program. There's not much it can do as far as changing the control flow. And possibly this is why the idea of blocking is maybe this handler didn't want any other signals to be able to interrupt it. So this handler can block signals. And in fact, what happens is every time a signal gets invoked, a handler, it automatically blocks that particular signal type. So you can't get a sort of unbounded loop of handlers being called, the same handler being called. And there's a kind of clunky way that you can set up these and specify which signals are blocked. There's instead of having you specifically changing these bit vectors, there's an API for it. Where you can create an empty set of blocks, meaning don't block any signals. You can block all signals by filling that set, or you can add specific signal numbers to the set, or you can delete specific signal numbers from the set. So these are all functions with various ampersands and arguments and stuff like that that you can use. But the idea of it is you can create and manipulate these sets of blocks. So here's an example of I want to block sigint. So I'll first create an empty, so I have to declare two sig set t's, which are whatever data structure it uses to represent these. And you don't need to know the details of how they're represented. But you can say create an empty mask, a mask where nothing is blocked, and then just add to it the signal for sigint, the bit for sigint. And then there's a function called sigproc mask, meaning change the signal proc mask for the set of blocked signals. And the idea is you pass in a pointer to the new set of signals, and you can also pass in a pointer that will then be set to the existing set of block signals. And so right now I'm running, this code will just be blocking only sigint. And if at some later point I want to unblock that sigint, what I'll do is I will say, okay, return back to whatever signals were blocked before. Resume back to what they are. And that's typical of what you do, that you want to sort of write your code that assumes that there's potentially some set of signals being blocked. I want to change that behavior, but then when I'm done, I want to resume back to the way things were before. So writing signal handlers has a lot of caveats to it. And some of the worst issues have to do with that there's, and so here's some guidelines that you'll have to follow. One is signal handlers need to be very simple. If they try to do too much, they should be they're designed to be just a very short piece of code to handle whatever that signal is and move on. They shouldn't be long-lived. They shouldn't traverse through some big data structure or anything like that. The other is that there's only a very limited set of functions that you're allowed to call in a signal handler. And it has to do with some very awkward interactions between the support for threading and signals. So threading is a way, we'll talk later in the term, that you can also create concurrent activities within a single process. Signals are a way to communicate between processes and create concurrent events. And they have some really bad interactions for some functions. We'll talk more later in the term about what those bad interactions are. But the bottom line is a lot of functions that you'd like to call, including printf or in sprintf, are not considered safe ones. So that code I showed you before is actually not good. The other is that there is a global variable called errno, which is the ID that's used to pass some information if an error occurs in a system call. And you're supposed to basically save that when you start the signal handler and restore it back. Because remember, any global variable that the signal handler accesses and changes will be permanently modified when the signal handler returns. You have to worry about blocking signals if there's potential for causing sort of race conditions or bad behavior between multiple signal handlers. And in general, if you use global variables, you should declare them as being volatile. Volatile is just a way to tell the compiler that when I give this global variable, I want it to really be in my program. Don't try to optimize it away. And potentially, you need to also declare them to be of type sig atomic t, which has to do with how the program is allowed to actually modify these values. And so this is actually really a nuisance. When you write signal handlers, there's a lot of stuff you want to do that you can't do. So in the book, they give a very small library of output functions to sort of replace printf that can print a string, a long, or some error message. And so the proper way to implement this signal handler I showed you for the bomb is to use these special versions of print routines that don't call printf. And also, it turns out you're not supposed to call the regular exit function. You're supposed to call one called _exit. Don't ask me why. I don't know that one. Okay. Now, here's another annoying feature about signals that's demonstrated by this example. So the idea of this example is I've got a loop that's going to fork off n children, and the child is just going to sleep for a second and then exit. So not much goes on, but you see this is a way to potentially create zombies. And so the idea of this is I'm going to use a signal handler. As these children exit, they will send sigchild signals to their parent, and the parent's going to receive those and know that, okay, I can reap this, I can make sure this child gets reaped by calling wait. And so the general idea of it is that there's this signal handler that's associated with the signal sigchild, and each time it gets invoked, it will wait for a process that presumably, and it will, in the process, then it will decrement this global counter, and then my main program will just sit there, apparently in an infinite loop. But what's really happening is, as this parent sits in this infinite loop, this child handler will be invoked for as many children as exit, and eventually that count will go to 0 and I'll be done. So that looks like it should work, but there's a problem with it. And the problem is this business that signals don't queue up. So if if multiple children exit and deliver their sig child to the parent before that signal handler gets fired up, this handler is only going to wait for one of them and reap one of them, and the rest of them won't. And what will happen is this program will potentially hang forever, because this count will never go to 0. It only goes to 0 once per call of the child handler, but that child handler might be getting called because there's been multiple children have exited. So it's this problem of not queuing, of just a single one. And so the correct way to handle it is to write a loop within the child handler that calls wait over and over again until it gets a value less than or equal to 0, which is the way that the operating system basically tells the handler, hey, there's no children that need to be reaped at this point, so give it up. And so you'll see that potentially this child handler might just reap one child, or it might reap the whole set of them, or any combination of those, and do that. And so this is an example then of how that handler could be used in my shell. So going back to the original example, remember that the idea of it, I had the shell, but it could create background processes, and the background processes didn't have any way of getting reaped. And so this handler here is an example of some code that handles that problem. And it's the same idea that we've just seen. It wait PID, if you give it a -1, it's the same as wait for anything. But it's being a little bit more careful. It's using, because there's some other data structure around there that the shell is using to maintain the set of jobs, and it wants to remove this process ID from that set of jobs. It wants to make sure that some other signal coming in doesn't mess up that data structure. So by blocking all signals while I'm doing this delete job, it's a way to make sure that no other signal handler is going to get fired up that potentially does anything with the same data structures that are here. So the idea in signal handlers is he is blocking as a way to prevent other signal handlers from getting called. So this example just keeps going on. And so this is I could talk for 3 lectures on this, but you can see you're going to have to read the book on this. And I would apologize for that. And but you will read the book about this, because this is going to be your upcoming lab. So you'll really get to know this. This is an interesting example of the same general idea of a shell, but it's got a kind of subtle and it's doing the same idea of creating a, wanting to start a bunch of children, each of which is going to run some program. And it will, and exec, this is sort of, remember exec will not return normally, so the children just disappear off after they've done this. But now the parent, you see, it will block all signals and add to the list of processes this particular process. So the idea of is I forked off a child, I executed some other program, and then I made sure that I added this program to the list of jobs that I'm actively monitoring. And then later that handler that we showed before will, when that process completes, then we'll delete this job. And you see I'm using this, I'm blocking signals as a way to make sure that I'm not trying to add and delete a job at the same time. But there's a problem with this program. And the problem is that the it sort of assumes that the parent is able to add this job, block and unblock the signals before the child executes and completes. But remember, as I've talked about before, there's no guarantee which goes first, the parent or the child. So potentially the child could run through this, execute this program, finish, and do all that before I've had a chance to even add it as to my list of jobs. So the basic idea is the correct way to handle this is to block sig child before you call fork, and then block all of them, add the job, and then go back and unblock everything. So, and then within the child, it has to unblock some of these too. So this use of blocking as a way to control what kind of events can happen is subtle and pretty tricky and pretty important. Okay, I have run out of time. But you'll find some pretty interesting quiz problems on Canvas, and we will pick this up next time.